And we've been talking about in this chapter thermodynamics, sort of the rest of the thermodynamics. We talked a lot about obviously the energy aspect of it, which is like the first law of thermodynamics in chapter 7. And here we got into some more aspects of it. Remember, when we talk about sort of thermodynamics, a lot of times it deals with whether or not, for example, a reaction will be sort of spontaneous or non-spontaneous. And as we talked about last time, remember that that really does basically refer to the idea of whether or not the reaction will actually just sort of take place. And again, it doesn't necessarily mean, as we talked about, that it happens really fast or it happens really slow. And again, sometimes people think about spontaneous as something just sort of happening really fast. And remember that the kinetics sort of takes care of how fast or slow. What we're a lot of times dealing with here in sort of this chapter and these sort of properties is the idea of just under those particular conditions, could be really fast, could be really slow, could be in between. Would we expect this reaction basically to take place? And if it does take place, then it is spontaneous. And one of the factors that we look at, in addition to, we look at delta H, which is our enthalpy. And obviously, as we've talked about a number of times, negative versus positive here, negative being exothermic, positive being an endothermic type process. We also can look at, as we talked about last time, the delta S. And the delta S is the change in entropy. And entropy really has to do with the amount of disorder there is. And entropy is a little bit different than maybe sort of what we normally think about things. As the amount of disorder increases, so does the change in entropy. Typically will become more positive. So the more disorder you have, the less order you have, the delta S typically will be a positive number. Opposite of that is obviously the less disorder that we have, or more order in that aspect. The delta S typically would be more of a negative value. One of the easiest places to see sort of the differences between sort of order and disorder is when we talk about things changing state. So when things go for, again, say solid to liquid to gas, these are all processes that increase the amount of disorder. As in the solid state, everybody is packed together pretty tight to one another. There's really not a lot of movement. In the liquid state, there is a little bit more movement. They have a little bit more energy, so things are moving. That's why they're able to pass. That's why they are basically liquids and fluid. And obviously in the gas phase, we got things flying around all over the place, creating a lot of disorder. And we would expect, as we kind of go in this direction, our delta S to be increasing, or again, becoming more positive. Opposite would be true if we were kind of heading in the opposite direction. We would expect a lot more order to be developing, and that would allow the delta S again to be a little bit more negative. Now, we can use entropy to help us decide whether or not a reaction will be spontaneous. And typically speaking, we use what is known as delta S of the universe. And delta S of the universe is basically made up of two things: delta S of the system or the reaction, plus the delta S of the surroundings. And if you were to calculate the delta S of the universe and it was a positive number, then that would mean that the reaction would be spontaneous, basically under those conditions. If you would calculate it, obviously, and it was negative, it would be the opposite. It would be a non-spontaneous type process. And if you happen to calculate it and it does equal 0, then you're really in a equilibrium type of system. And again, as we talked about, because it's an equilibrium, and basically you have the forward reaction and reverse reaction equal to each other, everybody pretty much gets locked into place. There really is kind of like no net change sort of happening in either sort of direction, and that's when it happens to be equal to 0. We do calculate these things two different ways. The delta S of the system or the reaction, you can look up, for example, in a table, and you can take the delta S basically of all your products minus the delta S of your reactants. And sometimes we'll see these little knots written next to letters and stuff like that. And that usually means when we kind of see these things like standard conditions and things are under sort of standard conditions. And when we talk about standard conditions, those are usually the situations that you have in tables. Like if we're talking about temperature, it's usually 25 degrees. If we're talking about any type of pressure, it's 1 atmosphere. If we're talking about a concentration, it's usually 1 molar. So when things are sort of under those kind of natural standard conditions, and that's usually the conditions that you find in like textbook values or table type values, that's what you would do. It's also important, as we talked about last time when we do this, that you also take the coefficient into account, and you would need to multiply by the values that you find in the table by the proper coefficient in the equation. So if you have 3 of something, you need to multiply the value you find in the table by 3 when you're doing it. The other thing that's different with delta S values, as we talked about, you will find in the sort of entropy table, you will find values for things in their standard state, like hydrogen, oxygen, just elements by themselves. And that's different than for delta H, which typically you find 0 for those values in the table. The other major difference, speaking of delta H and S, is the units, typically speaking. Kilojoules is typically the units that we associate with delta H. And a lot of times we are going with joules usually for our delta S. As I mentioned last time, and as we will see as we continue through this chapter, there will be a few formulas where we do use these values together, H and S. And again, we want to make sure that you watch the units. One of the places that we sort of saw that happen was last time as well when we talked about the surroundings. So to calculate the delta S of the surroundings, remember it's equal to negative delta H of the reaction divided by the temperature in Kelvin. And again, that temperature does need to be in Kelvin. And speaking of that units, typically, again, your delta H is going to be in kilojoules. So if you were to calculate your delta S of your surroundings and leave your delta H in kilojoules, you would have kilojoules for your delta S of your surroundings. And that could be problematic if you then go add it to your delta S of your, I guess I just circled the right thing, of your system there. Because that's going to most likely be in joules. So again, you're going to be off by that factor of 1,000. So you do want to make sure that you sort of watch those things. By the way, the delta S of the surroundings is related to the enthalpy of the reaction. As we talked about under sort of normal conditions, if you have an exothermic reaction, the system would be given off that energy to the surroundings. The surroundings would pick up that energy and create a lot more disorder, right? Everybody have a lot more energy in the surroundings from that energy coming from the system, and that would increase the entropy of the surroundings. Vice versa as well. If the surroundings were giving away some energy to the system, then the surroundings would lose that energy, and it would create a lot more order rather than disorder that occurs. Also remember that you do actually need to look at the delta S of the universe here to determine if it is spontaneous or not. Although we can calculate the delta S of the system, it will not necessarily tell us if the reaction is going to be spontaneous or not, but it will tell us, as we talked about last time, what's going on in the reaction. So as we talked about, if you create, for example, more gas molecules than you started with, you're going to create a lot more disorder than you had to begin with. And we would predict that the delta S for that reaction would end up being more positive in that case. If you actually create less gas molecules than you started with, then you would have a lot more ordered situation occurring, and we would expect the delta S of the system to be more negative in that case. Any questions on any of that stuff there? So I think I showed this and then I changed my mind at the end there. So let's talk about the third law of thermodynamics, which is, as I might have mentioned, the entropy of a perfect crystal is 0 at absolute 0 temperature. So clearly, if we look at the Boltzmann equation, which is another equation that we saw sort of earlier, and again, that is our entropy. That's our Boltzmann constant. And W is our microstates. So clearly, if we create a perfect crystal, there really is only one way to do that, and that would give us the natural log of 1, which is 0, and that would give us an entropy here of 0 in this particular case. Now, as we change phases of a substance, much like we talked about in the previous chapter, there is a certain amount of energy associated with those transitions. So if you remember, like we talked about in 7, I think, as we go from solid to liquid, or liquid to solid, that again does happen at the same temperature, which is your normal melting point or freezing point of a substance. The amount of energy required to do nothing more than, as we talked about, change the phase of a substance is the delta H of fusion. And if you remember, for something like water, it's like 335 joules per gram, or like 6.02 kilojoules per mole. And it would be a positive value, right? As you go from solid to liquid, and going in the opposite direction, it would be a negative value here, minus 335 joules per gram. Now, we also have that transitioning point here when we go from our liquid to our gas, which also happens at the same temperature, which is our boiling point. Going from liquid to gas, or gas back to liquid at the normal boiling point. That is our delta H of vaporization in terms of the energy that's associated with that. And that's going to be something like 2260 joules per gram going in the positive direction. Negative 2260 joules per gram are about 40.6 kilojoules per mole if we were talking about water, obviously, in this case. And that would occur at 100 degrees Celsius. So again, there is a certain amount of energy associated with that. There's also a certain amount of entropy change that occurs with that as well, as we do an entropy change as we go from solid to liquid, as we talked about, to gas. We obviously are creating a more randomness and disorder, so our delta S should be positive. And again, as we talked about last time, going the opposite way, again, our delta S here will be more negative going through that. Now, speaking of one of the sort of formulas before we move on here that we just talked about and that we saw last time, which is the delta S, by the way, of the surroundings. I might have mentioned it last time, or I might not have mentioned it last time, so let me just mention it now. This equation right here is the equation that you do want to use whenever you're calculating the delta S of the surroundings. Now, it should not be confused with something that we will see a little bit later on in this chapter, which basically will rearrange the exact same way as we have here, except there will be no negative. So that always messes people up. A little later on, we will see sort of this almost exact equation. When we rearrange an equation, the difference will be there will be no negative in the one that we'll see shortly. This one does have the negative, and the negative here is important because it gives it that opposite relationship as we talked about, that if a reaction is exothermic, that means the delta H will be negative, and negative will give us a positive delta S for the surroundings, which is what we would expect. And if a reaction is endothermic, the delta H will be positive. Positive and negative there is going to give us a negative delta S for the surroundings that we want. Later on, again, we will sort of see it. I'll point it out again when we get there. But we will again see the formula that looks very similar to that without the negative sign there. And again, try not to confuse those two. Any questions on that? Clearly, in the previous chapter, we also talked about calculating the energy, right, as we do phase changes and how we will always use sort of specific heat when we are changing the temperature, but the substance stays in the same phase. And we use something like the heat of fusion, heat of vaporization, where we change phases, but not temperature. So let's talk about the next sort of thermodynamic value, which is our friend Gibbs. And dare I say, I see a different letter there. So that's kind of nice. So Gibbs free energy is the change in free energy, which is delta G. And delta G is basically what the name implies. It is energy available to do some type of work, basically. And as we saw before in a spontaneous process, our delta S of the universe will be positive, and in an equilibrium process, it will be equal to 0. We will see, I don't know, maybe 4 different ways that have delta G in there and delta G calculations. The best piece of advice I could give you as we go through this is pick the appropriate equation based on the information given to you is probably the best choice. So for example, one way that you can calculate delta G is through this equation here, and that is the delta G is equal to delta H minus T delta S. So this is our Gibbs free energy. That is our change in enthalpy. That is our temperature in Kelvin. And that is our change in enthalpy, our entropy. That's our change in entropy there at the end. So this is, again, one of the sort of equations I was talking about before where you do want to be really careful with units. Once again, when you roll through this calculation, your delta H there is most likely going to be in kilojoules, your T will be Kelvin, and your S will be in joules. So once again, you do need to do some type of conversion there, or you will be off, like I said before, by that factor of 1,000. Doesn't really matter which one you do. I personally convert everybody to joules and then to kilojoules at the end, but you could go the other way. You could convert kilojoules and then just leave it in kilojoules. One of the nice things about Gibbs free energy is you could use it to predict whether or not a reaction is going to be spontaneous. And if the delta G is less than 0, I believe that means it's negative. The reaction is spontaneous the way that it is written in the forward direction. If you calculate the delta G and it is a positive number, that means the reaction, the way it is written, is going to be non-spontaneous, but some double talk. If you reverse the reaction, then it will be spontaneous. And that's because your products become your reactants become your products, all the signs change, and it'll go from being positive to negative if you reverse it. So if you end up with a delta G and it's positive, it's going to be non-spontaneous. If you end up with a delta G that's equal to 0, again, it is going to be at equilibrium. You also, again, like I said before, sometimes see this guy written with the little knots, meaning sort of, again, one way you can look at it is under sort of standard conditions, everything, like I said, 25 degrees Celsius, 1 atmosphere, 1 molar if you're dealing with some type of concentration. So as I mentioned a second ago, if you're laid up something like some delta H values, some S values, don't reinvent the wheel. Go into this equation to calculate delta G. Another way that you could calculate delta G, it is just like our other guys, which is we could do products minus reactants. So we could look up what is sometimes referred to as the delta G of formation or the standard free energy of formation. Those are values that you find in a table. So much like we could find delta H values in a table, we could find delta S values in a table. In fact, they're all pretty much in the same table. Usually you find the one that has the H, the S, and the G values all in the table, and you can look them up. You could look up the standard free energy of formation. So if somebody says standard free energy of formation, that's basically your delta G value that you can find in a table. And it is calculated like all the others. You basically, to calculate the delta G of your reaction, it is the delta G of your products minus the delta G of your reactants. And we would do the exact same thing that we do with delta H, with delta S, which is you also need to take into account the coefficient and multiply it by the number you find in the table. Once again, you will not find for delta G values for things like H2, N2, things in their standard state. Delta G and delta H are very similar in that aspect. They typically have 0 for those things. Again, it is just the entropy or S that you will actually find values for those type of things. As I've been mentioning, sort of our standard conditions, this is basically what it means when we talk about things under standard conditions. And again, that is typically what table type values are given to you in. And again, it is temperature 25 degrees Celsius. If you're dealing with any type of gases, like I mentioned before, it should have an atmosphere, 1 atmosphere pressure. If you happen to be dealing with any type of solutions, their concentration should be 1 molar. We will see in this chapter and a later chapter as well, when we have things that are not under standard conditions, there's a few different sort of formulas sometimes that you use in those set of conditions. And if something's off, like maybe the pressures are not all 1 atmosphere, or maybe the concentrations are not all 1 molar, there's some additional sort of calculations that we sometimes will do. Delta G, much like delta H, is also in terms of units, typically kilojoules. So typically kilojoules for delta H and G, and typically joules are the units that you have here for delta S. So again, those units very much mess people up when they do calculations because they forget there are different units when you grab these things. Any questions on that there? All right, so let's try one here. What is the standard free energy change for the following reaction? I think we have some values down here from like the table. O2 would equal 0 kilojoules per mole. Okay, let's take a look. We're looking for standard free energy. So that is our delta G. Not bad G. There. This is again a situation where pretty much this is probably all you're going to be given. So in a situation like this, clearly the first equation we saw with the H and the S is not going to do you much good. Here you would just go to the table and look up the values. Clearly that is where these values come from here. You go again to the back of the book, you can find your table. We're going to basically calculate our delta G of this reaction by taking our delta G of our products. Basically minus our reactants here. So we'll start here on our product side. We got 12 CO2s. Each CO2 is minus 394.4, looks like. We also have 6 waters. And again, you want to make sure you get the right water there. Minus 237.2. And that's going to take care of all of our products. We would then subtract it from our reactants. So we have 2 times our value there for our benzene, 124.5. And we would add it to our 15 oxygens, which they are all going to be 0, basically. Not too bad. So that is going to get us here 12 times minus 394.4 plus 6 times negative 237.2 minus 2 times 124.5. Looks like a negative 6405, I believe, and kilojoules in this case, right? This reaction is going to be spontaneous, not spontaneous. This reaction is going to be spontaneous as we have a negative delta G. So because of the negative delta G, this reaction will be a spontaneous reaction, which means we would expect this reaction to head in that direction, going from reactants to products as it is written now. Any questions on that one there? So this is a type of delta G problem where, frankly, you're just given an equation. Pretty much means go to the table, find the values, products minus reactants is the best way to calculate it. Any questions on that there? All right. Now, speaking of this equation, as I might have mentioned before, a lot of times in this sort of thermodynamics chapter, they will oftentimes, like I said, not necessarily give you numbers or values or anything like that, but they may just give you like, this guy is positive and this one's negative. Do you predict that this reaction is going to be spontaneous or non-spontaneous? So looking at this equation, we really can use it to help us sort of make a fairly good prediction. And the way we could do that is we also need to sort of think about units as well. So remember that our delta H is in kilojoules and our delta S is in joules, which means really our delta H has an advantage here. It's got like 1,000-fold sort of bigger sort of number probably than our delta S would be. So the first situation is we could have a delta H that is greater than 0. So that means that our delta H is positive. We could also have a delta S here that is positive as well. That means that this reaction, if you have a positive H and a positive S, this reaction will only really be spontaneous at high temperatures. And that is because the only way that this reaction becomes spontaneous is my delta G needs to be negative. And since this guy is about 1,000-fold jump on this guy, the only way to get this negative part larger is the temperature needs to be really high. And if you get a really high temperature, that will make the back part of the formula larger than the front part, and that will give you a negative delta G. Obviously, at low temperatures, you're not going to be able to beat the delta H value with this kilojoules, and that will give you most likely a positive value for delta G at low temperatures, and that would mean that the reaction would be non-spontaneous the way it's written at low temperatures. So in that situation, if we got positive on both, really our reaction will most likely only be spontaneous at high temperatures. Now, if we look at the next sort of option, which is, we'll look at this box here. In this box, we have the delta H is negative, so we got this guy is negative. And in the first row there, our delta S is positive. In this situation, because our delta H is negative and our delta S is positive and temperature is usually a positive number since it's Kelvin, that would mean no matter what you do to it at any temperature, you're going to hit a spontaneous reaction because everything's going to be negative. This guy's going to be negative. This part will be negative. And you will hit a spontaneous reaction at any temperature that you want. So sort of a really good sort of environment or situation for a reaction to be spontaneous is if you could have a negative delta H, sort of an exothermic reaction, and also a situation where you're increasing the entropy, right? And you get more of a positive one, which kind of goes together. If you think about it, more energy, probably more people flying around are moving around faster, more entropy, more positive entropy. So those things work, really well together. Now, if we look at the next sort of option on the table there, which is we'll go to this box here. And in this box here, we have a delta S that's negative. So we have this guy is negative, and we have a delta H that is positive. With our delta H being positive and our delta S being negative, that does what to the back end here? It turns this into a positive number no matter what you do, right? So no matter what you do at this point, you can put it at any temperature you like. You're pretty much going to have a positive back end of that formula with a positive front end of that formula, which means no matter what you do at any temperature, you're going to hit a positive delta G, and this reaction is going to be non-spontaneous at any temperature, the way it is written. You would need to make it spontaneous by reversing it, would be the only way to probably turn that thing around. You would have to reverse the reaction in that particular case. Any questions on that? Last sort of combination that you could have, sort of looking at this, which is, we have our last box there, just right here. We have a delta H that is negative, and we have a delta S that is negative. So once again, this negative delta S is going to turn this guy into a positive number. And that means that at really low temperatures, you will have a spontaneous reaction, because at low temperatures, this positive part is going to be less than the negative part, and that will keep your delta G negative. But if you crank up the temperature, you're going to be able to get this positive part of the formula to be larger than the negative part, and that will turn your delta G into a positive. So at low temperatures, you're good. It's going to be a spontaneous reaction. If you increase the temperature in that situation, you will end up probably with a non-spontaneous process sort of happening. So these are very common questions. Sometimes they're asked just based on sort of formulas, and this is positive, this is negative. You could also just throw in some numbers in there and sort of get some other values out. But this is the way you can sort of answer those type of questions. Any questions on that there? All right, then let's take a look at this. Let's say we have this reaction here of carbon, calcium carbonate, they call that, I think, decomposes into a little calcium oxide and a little carbon dioxide gas. This reaction is a delta H value of 177.8 kilojoules and a delta S of 160.5 joules per Kelvin. Why don't you calculate the delta G naught at 25 degrees Celsius? So what would be the delta G of this reaction at 25 degrees Celsius? And is it spontaneous at 25 degrees Celsius? So, okay, let's take a look. So again, here we have H, we have S. So probably the good calculation would be delta G is equal to our delta G naught is equal to delta H minus T delta S. There we go. And obviously we do need to convert our temperature into Kelvin. So we're going to add a 273, going to give us a 298 Kelvin. We're going to put it in here, take our delta G naught is equal to 177.8. I'm going to multiply it by 1,000. And the reason, again, I'm multiplying by 1,000 here is that's going to convert it into joules for me. And I want to do some type of conversion because my S is in joules. Otherwise, again, we are off in terms of our units. So I'm going to convert the front end here to joules. I then will subtract it from 298 Kelvin times my delta S, which is 160.5 joules per Kelvin there. That's going to get me 177.8 times 1,000 minus 298 times 160.5. It's going to give me a 129971 joules. Or if I divide it by 1,000, about 130 kilojoules, which again is typically the units that we see for delta G. Again, just dividing by 1,000 there at the end of my bad J at the very end of that sentence there. First off, any question on the calculation there? J. All right. Is this reaction at 25 degrees spontaneous or non-spontaneous? It is non-spontaneous, such our delta G here is positive. So at 25 degrees, no luck. It is a non-spontaneous reaction. Right? So this reaction happens to be non-spontaneous at 25 degrees. can I figure out at what temperature it will become spontaneous? And the answer is yeah, we could actually use the same formula to figure out at what temperature we would need to sort of turn this non-spontaneous reaction into a spontaneous reaction. So if we take our same formula there that we were using, which is our delta G naught is equal to delta H minus the, I can't say it anymore, delta S here. We know that the delta G needs to be negative, and negative is on the other side there of 0, right? So if we create delta G is equal to 0, gives us delta H naught minus T delta S. Bringing this whole guy to the other side gives us T delta S equals delta H, dividing by delta S to the other side. I'll come over here, dividing delta S here to the other side. That's going to give me the temperature is equal to my delta H divided by my delta S. And I have both of those numbers, so let me put those numbers in and see what we get. Once again, we still have unit issues here, so you need to do some type of conversion. I am again going to multiply my delta H by 1,000 to turn it into joules. And I'll leave my bottom guy in joules. Joules will cancel correctly. Again, a situation where you do not want to go in with kilojoules on one and joules on the other. We're going to divide it out there, about 60.5. We'll call it roughly there, 1108 Kelvin is the temperature at which it turns spontaneous. Minus a 273 gives us an 835 degrees Celsius, which I would say is fairly warm, I suppose, yes, in terms of a temperature. And surprisingly, not unsurprisingly, here we see on the graph, this is a graph of the pressure of carbon dioxide, which is the only gas produced in this reaction. And since it's a product, the only way we can produce the pressure is to produce the product, which means the reaction has to happen. It actually really doesn't pick up there until we get to 835, which is right about here. Now, you may say it does pick up a little before that, and you're correct. But at 835 degrees temperature, the pressure actually hits what pressure? 1 atmosphere, which is standard pressure. So it hits standard pressure at about 835 degrees Celsius. It does pick up a little bit higher than a little bit before that, but it really doesn't reach sort of standard pressure until about 835. So this equation can be used, obviously, as we did the first part of this, which is just to determine whether or not a reaction is going to be spontaneous under those conditions. And if it happens not to be spontaneous under those conditions, you could also try to calculate the temperature at which it would turn spontaneous under those conditions. Questions on that there? By the way, if we think about what we just talked about on the previous slide, in this situation, we had a positive delta H and a positive delta S, which, as we talked about, the only way for this back end to beat the front end is you need a really high temperature. And I would say, once again, 835 degrees would account for a high temperature. And that's enough to get this back end to be more negative than the positive front end. Not sure if that's really words, more negative, but we'll go with it. Yeah. Any questions on that there? So that's what we were talking about a second ago on the previous slide. Positive on both of them. We would expect what we got in the first calculation, which is a regular sort of normal temperature. A low temperature is going to be non-spontaneous. You need a pretty high temperature to turn it into spontaneous reaction. All right, try this one here for the following reaction. Delta H is negative 1204. Delta S is minus 216. At 25 degrees, are there reactants or products? We have an H and an S given to us. We want to know really, if this reaction is going to be sort of spontaneous. Are the reactants or products favored? So delta G is a good one to use. And again, I would use this version of obviously the way to solve it, since we have H and S. We need to, like normal here, just convert our temperature there to Kelvin. Going to get us at 298. That's going to give us a delta G naught. Once again, I'm going to multiply by 1,000 to convert my kilojoules into joules. we're going to subtract 298 times my delta S, which is already in joules. So everything works out perhaps nicely. And that's going to get us there, negative 1204 times 1,000 minus 298 times negative 216.4 or 9 if you punched the wrong number in. Let's try that again there. Minus 298 times negative 216.4. That might be better. That's going to get us here negative 1139512.8 joules. And divide it by 1,000 and take it back to kilojoules. Do a little rounding there. Negative 1140 kilojoules. Sounds good to me. First off, any questions on the calculation there? Again, we're dividing by 1,000 on the back end here to get it to kilojoules. Reaction going to favor reactants or products? Reaction spontaneous or non-spontaneous, basically. Delta G is, yeah, so delta G is negative, so essentially it's spontaneous, and if this reaction is spontaneous, the way it's written, it should be heading in the forward direction, right? Which means we would favor products in this case, yeah. Any questions on that one there? Now, again, if we look at sort of our equation or formula here and what was given to us, we did have a negative delta H. We had a negative delta S. That negative delta S turns this back end into a positive number, which means as long as we're at a low temperature, the back part of the formula can't get large enough to beat the front part. And that's what we had here, right? So we had a regular kind of temperature at 25 degrees, a relatively low temperature. Which means it's going to keep the back end of the formula smaller than the front end, and we got a negative number. Again here, if we did this at a really high temperature, we would maybe have a non-spontaneous reaction, right? As the back end there would be able to maybe overcome the front end in terms of the numbers, yeah. Yeah, so if it's positive, essentially it's going to be essentially like a non-spontaneous reaction, which means the way it's written, it's pretty much not going to go to the right. So it's just going to hang out over there on the left, and reactants would be favored in that case, yeah. Other questions? So we talked a little bit earlier about phase changes and Gibbs free energy and phase changes. So let's talk a little bit about that and the entropy of phase changes. So as we've talked about before, phase changes happen at the same temperature, which means they are equilibrium processes, right? And that's because at exactly, for example, 0 degrees Celsius, you have ice crystals. You got a little bit of solid, you got a little bit of liquid happening. You got both phases in equilibrium with each other. Same thing happens as you go from liquid to gas. You got basically both phases happening, say at 100 degrees Celsius for water at the normal boiling point. And again, it's at equilibrium. And as we talked about earlier, if you are at an equilibrium type condition, your delta G is going to equal to 0. So when we do this phase change, which happens at the normal boiling point of water in this case, that is liquid water going to steam, right? Basically evaporating is what's happening here. We're going sort of in this direction. So we can rearrange our delta G equation here and solve for S. And by doing so, we take T delta S is equal to delta H. And in this case, we're going to divide the T to the other side. And we will get that delta S is equal to delta H naught divided by our temperature, which does need to be in Kelvin, by the way, like normal. This is what is called, in this particular case, the delta H of vaporization, delta S of vaporization. This is the delta S of vaporization. This is the equation that I was just talking about not too long ago. That equation looks pretty much identical to this equation, which is the delta S of the surroundings. This is what I was talking about a second ago. The difference is the negative. Negative there, no negative here. People always want to put the negative on this one. So you do not do the negative on this one when you're doing some type of phase change. And essentially that equation is coming from rearranging this equation. So you want to be really careful with that. Where do we get these numbers? Well, this number right here is our delta H of vaporization for water. And the normal boiling point of water is 100 degrees Celsius, right? And if I add 273 to that, I get 373 Kelvin, right? So that is the normal boiling point of water. We calculate the delta S of vaporization for this process, and it is positive 109 joules per Kelvin. Does that make sense in terms of what is happening as we go from liquid to gas? Should the entropy be positive? It should be, right? Because as we go from liquid to gas, we're going from a more ordered state in liquid to a more disordered state, right, in the gas state. And that should give us a positive value for delta S. By the way, if we were actually going in the opposite direction, like the delta S of condensation, right? What would be the only difference here? If I was going from gas to liquid. Temperature would still be the same, right? Because it's still 100 degrees. The difference would be my delta H of vaporization should be negative in that case, right? It's exothermic, right? As you go from gas back to liquid, it has to give off energy for those gas molecules to slow down and enter the liquid phase. That would then turn, if we were going in the opposite way, like a delta S of condensation, for example, my delta S value would then be negative, which also makes sense, right? Because we're going from a gas state of more disorder to a liquid state of more order. This is also why you don't include the negative in this formula, because that will screw up that whole calculation you just did right there. Yeah, so that's why we don't have the negative here. You would put the negative in depending on which way you're kind of going. If it's really not specified and they maybe just give you the delta H of vaporization, probably 9 times out of 10, or even more than that, is probably safe to assume you're going from liquid to gas. They probably would specify somewhere if you're kind of swinging the other way, going from gas back to liquid, or to mention something about condensation. By the way, you could also do this like the delta S of fusion, right? Could also happen, and that fusion would be when we go from solid to liquid, liquid back to solid. The only difference in the calculation here would be we would use the delta H of fusion, yeah, over the temperature. And again, for water, that would be like the 6.02 number divided by 0 degrees Celsius, which is 273 Kelvin, right? And that would be the temperature. Positive going from solid to liquid, negative going from liquid back to solid in this particular case. Any questions on that? Also, if we were not dealing with water, you should make sure you have the correct delta H of vaporization and fusion for whatever substance you're dealing with. And you should also have the correct boiling point temperature and melting or freezing point temperature, as if it is not water, it will not be 0 and 100, right? So it'll be different values. All right, so why don't you try one here? The enthalpy of vaporization for mercury is 58.5 kilojoules per mole. The normal boiling point is 630 Kelvin. All right, so we have enthalpy of vaporization, and enthalpy, not to be confused with entropy, is our delta H of vaporization. That is for mercury, as we can see, is a different number. Also, because it's mercury, it again has a different boiling point temperature. So we're doing the transition there from liquid to gas. We could look at our delta G equals delta H minus T delta S. Once again, because it's going to be an equilibrium type of situation, our delta G here is going to equal 0. And this is how we can, again, rearrange this equation to solve for the entropy. We'll subtract that to the other side and then divide our temperature over. That's going to get rid of that. That'll give us our delta S is equal, once again, our delta H divided by T. Putting this in will give us 58.5 kilojoules divided by our temperature, which is already in Kelvin, which is nice. And that's going to get us there 58.5 divided by 630. Something like 0.0929 kilojoules per mole per Kelvin. If you want it in joules, you'll have like 92.9 joules if you calculate it. Yeah, in that case. Here it would be positive under the assumption, obviously, that we're going from liquid to gas. Again, if something was mentioned about condensation, once again, the only thing that would change really is the sign of the delta H, and we would turn it into a negative value. Any questions on that there? All right, then let's talk about Gibbs Free Energy and our friend equilibrium, because it's been a long time since we've seen our friend K. We can't go too far in this class without it. So let's talk a little about the equilibrium constant, but let's also talk about a situation that can develop. As I mentioned before, typically when we do things under standard conditions, we're talking about, again, sort of table type situations where we have, again, the temperature is 25 degrees, pressure 1 atmosphere, the concentration is 1 molar. That, again, is basically what the little naught sort of stands for here. And that means in this equation, we have a delta G is equal to delta G naught plus RT natural log of Q. The way you could look at these values is that is your delta G value under kind of non-standard conditions. So what does that mean? It means that maybe the temperature is not 25 degrees. Maybe you have pressures that they're not all 1 atmosphere. Maybe you have concentrations where they're not all 1 molar. So something is not under standard conditions, and that is what sort of that delta G you could think about is. This delta G naught is our regular kind of products, minus reactants under standard conditions that you look up in the table, which is under standard conditions. Our R's are gas constant, but it's actually the one that involves energy, 8.314 joules per Kelvin per mole. Our temperatures in Kelvin. And a also throwback from the past there is Q. Q is our reaction quotient, right? And remember that Q is calculated the same as K, which means Q is our products over our reactants. This also is like normal. If you have a coefficient, it becomes the exponent, just like you would calculate the K. You would do the Q the exact same way. So you also want to make sure you take into account those things. So yet another delta G sort of equation, if you will. And this one, logically speaking, is one where, frankly, you do not have standard conditions. So most likely in a problem, they'll give you some pressures that are a little bit different than 1. They'll give you some concentrations that are probably different than 1. And that's a good key that's probably the right one to use in that particular case. Sometimes they may actually just give you the delta G naught in the problem. Sometimes you may have to still calculate the delta G naught by going to the table. So it does sort of depend on the situation. Now, if we do hit equilibrium, as we talked about before, which is a process where delta G will equal 0, the top equation, the G equals 0, the Q equals K, and if we rearrange it, we get yet again one more delta G equation because we don't have enough of them. So this is delta G naught is equal to minus RT natural log of K. And that is still the same as above. So that's our 8.314 version of our gas constant. That is still our temperature. And of course, K is our equilibrium constant. So again, logic tells us that if it had mentioned something about the equilibrium constant, gives you an equilibrium constant, asks you to solve for an equilibrium constant, that would be your winning equation right there, yeah, to use. So this is what I was kind of saying earlier. The best piece of advice is use the equation that has delta G in it that is kind of appropriate for the information given to you in the problem. If you're not given any type of information other than the equation, and they ask you to calculate delta G, go to the table and do products minus reactants. If they're nice enough and give you a delta H or delta S, then throw it into the one that has the H and the S in it. If they have something to do with equilibrium constant, go to this equation. And obviously, if we have some type of non-standard condition, equation up there on top. So that's probably the simplest way to just think about it as to, which one should I use in which situation. A lot of times the question itself sort of determines, which one that you want to use. Any questions on that there? So that's a lot of graph there that I don't want to look at right now. So let's take a look at this one right here. This is the equation. And the nice thing really about this equation here with our K value in there is, frankly, if you still know what K means, which I hope you do, you could pretty much still figure out everything like normal. So obviously, as we know, if we have a large value of K, we would expect obviously more products at equilibrium. And really the only way to get products at equilibrium is for the reaction to be spontaneous and heading towards the products. And we would expect a negative delta G in that particular case. By the way, there is a negative in this one, yeah? And the other one, by the way, is a plus, which people always want to subtract, yeah? So watch out on that one. People always want to subtract that one particular one. Now, if we have a small value of K, as we know, that means that when we reach equilibrium, we should mainly have reactants. And if we mainly have reactants at equilibrium, that reaction is pretty much hanging out over here on the reactant side and not going very far. And that would mean that the reaction is going to be non-spontaneous most likely and have a positive delta G value in this case. If we have a K value that's equal to 1, it's a toss-up. You could go either way because you probably have equal numbers of reactants and products at that point, which means it's not really favoring one way or the other. The difference is probably going to be relatively small. Any questions on that there? All right, we're going to lay it up there for today because the sun